Yes, in a three-phase, four-wire, 120/208 volt system, the neutral conductor is typically counted as a current-carrying conductor when the building contains computers and electronic ballasts due to the presence of harmonic currents. Electronic devices like computers and electronic ballasts generate harmonic currents, specifically third harmonic currents and multiples thereof, which are additive in the neutral conductor. In a balanced linear load scenario, the neutral conductor would ideally carry little to no current. However, with significant harmonic distortion, the neutral current can become substantial, potentially exceeding the phase currents. Therefore, it is crucial to consider the neutral conductor as a current-carrying conductor in these situations to ensure proper conductor sizing and prevent overheating. Sizing the neutral conductor appropriately is essential for safety and reliability. The National Electrical Code, or NEC, provides guidance on conductor sizing, including adjustments for the number of current-carrying conductors in a raceway or cable. When the neutral conductor is considered a current-carrying conductor, the ampacity of the phase conductors must be derivated according to NEC Table 310.15 current, formerly known as NEC Table 310.16. This derivative accounts for the increased heat generated by multiple current-carrying conductors in close proximity. In addition to computers and electronic ballasts, several other factors can lead to significant neutral currents. Firstly, nonlinear loads, such as variable frequency drives and uninterruptible power supplies, generate harmonic currents similar to computers and electronic ballasts. These harmonics contribute to the overall neutral current and must be considered in conductor sizing. Secondly, unbalanced loads, where the current drawn each phase is significantly different, can also cause substantial neutral currents. Even without harmonics, an unbalanced load will result in current flowing through the neutral conductor to compensate for the unequal phase currents. Thirdly, long feeder runs can exacerbate the effects of harmonic currents and unbalanced loads. The impedance of the neutral conductor increases with length, leading to higher voltage drops and increased current flow in the neutral. It is important to calculate the voltage drop and ensure it remains within acceptable limits, as specified by the NEC. When assessing the neutral current, it is essential to use appropriate measuring equipment, such as a true RMS ammeter, which can accurately measure non-sinusoidal waveforms. Standard ammeters designed for sinusoidal waveforms may not provide accurate readings of harmonic currents. Furthermore, it's important to perform a load analysis to determine the expected current draw of all connected equipment, including computers, electronic ballasts, and other nonlinear loads. This analysis will help determine the appropriate size for the feeder conductors and the neutral conductor. The NEC provides guidelines for calculating feeder sizes based on the connected load. In some cases, it may be necessary to increase the size of the neutral conductor beyond that of the phase conductors to accommodate the expected harmonic currents. This is particularly important in buildings with a high concentration of electronic equipment. Another consideration is the type of wiring method used. The NEC specifies different ampacity ratings for conductors in different wiring methods, such as conduit, cable tray, and free air. The ampacity ratings are based on the ability of the wiring method to dissipate heat. It is important to select a wiring method that is appropriate for the expected load current and the ambient temperature. Furthermore, the NEC requires that conductors be protected against overcurrent by fuses or circuit breakers. The overcurrent protection devices must be sized to protect the conductors from overheating due to excessive current flow. It is important to select overcurrent protection devices with the appropriate ampacity rating and interrupting rating. Grounding is another critical aspect of electrical system design. The NEC requires that electrical systems be properly grounded to provide a low impedance path for fault currents. A properly grounded system helps to protect against electric shock and equipment damage. The grounding system should be designed and installed in accordance with the NEC requirements. Surge protection is also important, especially in buildings with sensitive electronic equipment. Surge protection devices can help to protect against voltage surges caused by lightning, switching transients, and other events. It is important to select surge protection devices with the appropriate voltage rating and surge current capacity. Energy efficiency is another important consideration. Selecting energy-efficient equipment and implementing energy-saving measures can help to reduce energy consumption and lower operating costs. The NEC provides guidelines for energy-efficient design. Proper maintenance is essential for ensuring the long-term reliability and safety of the electrical system. Regular inspections and testing should be performed to identify and correct any potential problems. Maintenance should be performed by qualified personnel in accordance with the manufacturer's instructions and the NEC requirements. Finally, documentation is critical. Accurate and up-to-date documentation of the electrical system, including drawings, specifications, and maintenance records, is essential for troubleshooting and future modifications. The documentation should be readily available to qualified personnel. In summary, when designing and installing electrical systems in buildings with computers and electronic ballasts, it is crucial to consider the effects of harmonic currents on the neutral conductor. The neutral conductor should typically be counted as a current-carrying conductor, and the feeder conductors should be sized accordingly. Other factors that should be considered include nonlinear loads, unbalanced loads, long feeder runs, wiring method, overcurrent protection, grounding, surge protection, energy efficiency, maintenance, and documentation. By carefully considering all of these factors, it is possible to design and install a safe, reliable, and energy-efficient electrical system. Now, to be more specific about the NEC requirements that relate to the neutral conductor as a current-carrying conductor, there are a few key sections to be aware of. NEC Section 310.15b5, previously known as 310.10, addresses the conditions of use for conductors. It specifies that neutral conductors carrying only the unbalanced current from other conductors of the same circuit do not need to be counted as current-carrying conductors when determining ampacity-derating factors. However, there's an exception to this rule that comes into play when dealing with nonlinear loads. That's where the third harmonic and other harmonic frequencies come into play. These harmonics can cause significant current flow in the neutral conductor, even when the load is balanced. In these cases, the neutral conductor must be counted as a current-carrying conductor, and the ampacity of all the conductors in the raceway or cable must be derated accordingly. As an example, consider a three-phase, four-wire system feeding a panel board that supplies power to a large number of computers. The computers are considered nonlinear loads because they draw current in short pulses, which creates harmonic frequencies. The third harmonic current and other harmonic multiples will add up in the neutral conductor, potentially exceeding the current in the phase conductors. In this case, the neutral conductor would be counted as a current-carrying conductor, and the ampacity of the phase conductors would need to be derated based on the number of current-carrying conductors in the raceway. NEC Section 220.61 provides guidance on calculating the neutral load for service and feeder calculations. This section specifies that the neutral load must be calculated based on the maximum unbalanced load, but it also requires that the neutral load be increased to account for any expected harmonic current. In many cases, it's difficult to accurately predict the amount of harmonic current that will be present in a particular installation. Therefore, it's often best to err on the side of caution and assume that the neutral conductor will carry a significant amount of harmonic current. This will help to ensure that the neutral conductor is adequately sized and that the electrical system is safe and reliable. In addition to the NEC requirements, there are also some industry best practices that can be followed when dealing with neutral conductors in systems with nonlinear loads. These include using oversized neutral conductors, using separate neutral conductors for each phase, and using harmonic filters to reduce the amount of harmonic current in the system. Oversized neutral conductors can help to reduce voltage drop and improve system performance. Separate neutral conductors for each phase can help to reduce the amount of harmonic current that flows in the neutral conductor. Harmonic filters can be used to reduce the amount of harmonic current that is injected into the electrical system by nonlinear loads. These filters work by trapping the harmonic currents and diverting them away from the neutral conductor. When selecting a neutral conductor, it's important to consider the following factors. Firstly, the expected current carrying capacity of the conductor. Secondly, the ambient temperature. Thirdly, the type of insulation. Fourthly, the type of raceway or cable. And fifthly, the length of the conductor run. The current carrying capacity of the conductor must be sufficient to handle the expected neutral current, including any harmonic currents. The ambient temperature can affect the ampacity of the conductor, so it's important to select a conductor that is rated for the expected ambient temperature. The type of insulation can also affect the ampacity of the conductor, so it's important to select a conductor with the appropriate insulation for the application. The type of raceway or cable can also affect the ampacity of the conductor, so it's important to select a raceway or cable that is suitable for the conductor and the application. The length of the conductor run can affect the voltage drop, so it's important to calculate the voltage drop and ensure that it is within acceptable limits. By carefully considering these factors, it is possible to select a neutral conductor that is properly sized and will provide reliable performance.